Hello, ladies and gentlemen. So this is Monday, January 22nd. So this is wrong. Let's get this right. 22nd. All right, and this is asynchronous. If I can write this down, there we go. So this is an asynchronous meeting. So what we're going to be doing is talking about position. This is our motion unit. All right, so motion, we're going to first start with position. So this is 1.1, so the start of our motion unit. In our motion unit, we're going to be talking about motion, distance versus displacement, scalar versus vector. And why are we going to do that? To understand the quantities that describe motion to prepare for studying velocity and acceleration. So this is the information that we're starting you off with. You may know this already, but science has a way of using strange vocabulary to explain things. And a lot of times, like right now, displacement is not something that people understand. It was probably the most challenging part of the last year's unit. Scalar versus vector, people had get those confused. So my suggestion is that we use flashcards, notes, and do some practice. Okay, we will do practicing in Pear Deck, right? We also use Blooket. But again, it depends on you and how much you engage in the unit, right? If you're checking the notes, doing the assignments, watching the recording. So it's important that you do that to get a clear understanding of this stuff. So let's look at our ideas of motion, distance versus displacement, and scalar versus vector today, okay? So are you moving right now? Me, I'm just sitting in a chair, so I'm just sitting, but my arm is moving, so as I'm writing, so my heart is beating, right? But for the most part, maybe I'm fidgeting around. But let's think about you may have hard time sitting. Maybe you're watching this or listening to this while you're walking around. Um, Maybe you stop and start because you're hungry. Now, if we think about motion in the universe, everything in the universe is moving. All right, so accelerating through space at tremendous speeds, that means it's moving faster or slower. Okay, so it's faster, going faster and faster and faster, or maybe it's slowing down. Tremendous speeds, so 300,000 kilometers a second. That's the speed of light. Okay, and even though the speed of light is that fast, quite a big distance, that we still have to measure because the universe is so large. We have to measure things in light years. How far something goes in at 300,000 kilometers per second in a year, and the distances between planets um, or galaxies is so fast, far away that would take thousands of years in many cases to get anywhere. So motion, again, this is our vocabulary word, is the process of changing position, right? So you have a tree here and you go to the stop sign, let's say. All right, so that's your distance. Okay, we have some positions or we have some reference points there. That's a reference point. We have the tree and the stop sign. And again, you may have took a turn to challenge your brother, one of your siblings, to a race. So we got to have a starting point and a stopping point. All right, so frame of reference is a set of points or objects used to determine relative movement. Relative movement. So we need to have something to tell us that we are moving. And if you were in space, and there was nothing around you, it would be very hard to tell if you were moving at all because you have nothing to see. You find that in the case of in the ocean, or you can't tell if you're moving because you have nothing to see if it's getting bigger, like the land. You're getting closer to the land, let's say. You can tell that the land is getting bigger or something's coming closer to you. All right, so let's first talk about distance versus displacement. So distance is the total pathway, and the total pathway is this. Let's say this is my start, right? My start place as 1, and I'm taking traveling this kind of curved route. And you may have done this, especially if you've gone to Hocking Hills or something. Like I love to go to Hocking Hills, and you take these long routes because there's so many hills, there's so many uh, obstacles in the way, large rocks and so forth that we can't move when we make the road, that we, in order to get from one place to the other, we have to make these route changes, right? And so I have this blue line, which shows a path. Okay, total, this is the length of a total pathway. So let's say I wanted to get to a particular cave in at Hocking Hills, and I have to drive all this way. All right. So that's my total distance here. Total distance is the blue line here. Now, if I was a bird, let's say, and I could get from 1 to the end, 2, I could forget about these obstacles. I didn't have to go this curved path, and I could fly across. Maybe one of these days we'll have our own little personal flying drones that we can fly, and we don't have to worry about the roads. Especially this time of year, it's so icy that getting outside, if you're learning to drive, is kind of dangerous, right? So the blue line, and you can see my words in blue, is the total distance, all right, between 2 points. And the displacement, now here is the part that people have the most trouble with. They have this idea of displacement, and displacement is the length of a straight line between 2 points. So start and finish, all right, is the displacement. So in science, we're concerned about how far is it between the starting point and the ending point in the shortest distance possible, which is a straight line. So which color represents the distance between points 1 and 2? So if you remember, so if I'm asking this question, so is it blue line or the red line? Right? So blue line question or the red line, which is it? So if you pick blue, you're correct. That whole distance between the start and the finish is the blue line. Okay. Right. So it is possible for the start and finish to be different than this. I'll get to that a little bit later here. All right. So that is my distance between the start and finish, the blue line. So displacement, remember, is the shortest distance between 2 points, the start and finish, the straight line there. And remember, that is that red or blue? Is that a blue or a red? And in this particular case, it's the red line, right? Red line is the displacement, the distance between the two. All right, so let's take a look at distance versus displacement here. All right, so let's take a look at a start and finish line. And these are short distances here, 5 meters. You could actually walk this in your room. 5 meters is about a little more than 15 feet. So if you have a large enough room, you could do this. So if we're going to go west, now the reason that we're talking about displacement is we also talk about direction, right? Direction. Okay, my screen does not work really well at drawing today. Screen has been used quite a bit, so it does not draw very well. Okay, so speed. So this is the direction I'm going. Okay, so I'm going, let me see if my finger works well. I'm going to go 5 meters this way to the west, because if you think about here, this is my north, west is to the left. Then I'm going to go north 1 meter, and then east 1 meter, 5 meters, sorry. So I got 5, 1, and 5. So what is the distance here? What is the distance? Remember, that's the total distance around here, right? So the answer to this would be 5 plus 1 plus 5, or 11 meters. $11. Okay. And we use the unit M for meters because that's what we're talking about. We just said 11, right? So what does that mean? It doesn't tell us how far that is. It just tells us a number. So displacement is this distance between the start and finish, the shortest line, the line between the start and finish. And in this particular case, what would you say this was? All right, I'll let you answer that question. Give us a few minutes there. That'd be 1 meter, right? Just the distance between the start and finish. Let's try another one here. What's the distance if you go, so remember, I'm going to use my north as going up, start and finish. So here's the start. See, notice the start and finish is the same place. So start, we're going north 3 meters. So we're going this direction. Here we go. 3 meters this way because we're going north. Now we're going 5 meters this way. Then south 3 meters. And then east 5 meters. So we end up back where we started from. So we ended up back where we started from. So if we add those together, so 3 plus 5, 5 plus 3 plus 5. Okay, we've got 16 meters for my distance. Okay, 16 meters for my distance. But let's take a look at displacement now. Remember, it's the distance between the start and the end in the short distance here. Now notice it's the same place. So I have no distance between the start and because they are at the same place. So the start and the finish are on the same spot. So what would that give you? If they're start and finish on the same spot, I want to know the distance between the two. What would you say that was? All right, so if you came up with 0 displacement, you're correct. Right? So let's take a look at this real quick. Right? So if for some reason, okay, so when the displacement is 0, if the start and finish are the same spot. But let's say that my start and finish where the, oh, here is my finish and my start is here. So if I go 3 meters here, okay, and that was my finish, so it's possible that the distance can be 3 meters. And also my displacement can be 3 meters. So it's possible for my distance and displacement could also be the same. Could be the same. Could be the distance could be a number and the displacement could be 0. So it is possible for distance displacement be the same, but it's also possible for the distance to be a number and the displacement to be 0. Can the distance ever be greater than the displacement? Sure. Sure it can, right? So think about a baseball diamond, right? So we have the home plate, first, second, third. And let's say they're 90 meters apart, every single one. So my distance to first base, if I were just to go to first base, my distance and my displacement, I'll put just dP, could be 90. They're both the same between the distance between home and first base. Okay. So, but my distance between first base, home, and for a home run would be 90, 90. Let's do this again. 90, 90, 90, and 90. So 9 times 4 is 360. But my displacement is 0 because I ended up where I started from. Can the distance and displacement ever be the same? Yeah, sure. Okay, remember I said, got your diamond, right? First base, 90 feet. Home plate, so it can be the same. All right, so scalar versus vector quantities. Scalar is a quantity that something is measurable with just a number. So the magnitudes is another vocabulary word, means size or number. I always think about magnitude when we talk about earthquakes. Earthquake magnitudes have numbers by them. So the higher the number, the stronger the earthquake. So, so quantity, so something that has a measurement of, so let's say 1 mile, okay, is a magnitude, right? And that is considered a scalar. Scalar involves magnitude only. So a scalar is 1 mile. So a vector is a quantity that involves both magnitude and direction. So all I have to do is I went 1 mile north, and now I have a vector. So I have to have both of these in order to have a vector. A vector you can usually see as an arrow, right? So in science we use arrows to determine the magnitude. So the longer the arrow, the longer the distance. Okay, so if this is 10, and again, I'm going, if I look at this, I'm going, this is north, now I'm going kind of northeast. So we use arrows in science to be our vectors. And scalars are just magnitudes only, right? So we don't use an arrow, we just give a number to it. 1 mile, 50 feet, right? Anything that has a size or an earthquake magnitude 9.5, pretty devastating earthquake magnitude. What's something that would be a scalar quantity? Okay, as I said, feet, meters, all right, miles per hour, meters per second. Those are all scalar quantities, all right? So those are some things that we think about. Meters per hour, so we have no direction in those. So vectors, we talk about acceleration. Acceleration is a vector because things are slowing down or changing direction. So acceleration, meters per second squared. If you see something like that, that's an acceleration, and it's automatically considered a vector. Or meters per second north, right? Or an arrow that says a 10 by it and it's east, right? So those are combinations of vectors, okay? So meters per second. Also, gravity. When we think about gravity falling to the earth, okay, so falling, we're going down, okay? Or we can be going up, okay? If we're going up or down, because gravity is always pulling down on us, that's a vector as well. Okay, so examples of scalars and vectors. Scalars only magnitudes. It's speed, weight, age, temperature, distance. Vector, both magnitude and direction, represented by arrows pointing in the specific direction. Length of arrows represents the magnitude. Examples: velocity, force, acceleration, momentum, and displacement. Example would be 55 miles per hour north. And we'll be talking about force and momentum in the next sections. So just to let you know. So which of these vectors would be the greatest magnitude? Is it the red one or the blue one? All right, so the size matters here. So we're talking about the vector here, right? So this one, let's say this is 10 and this is 5. That's a lot of times to give you numbers on here. The blue one would be the one that has the greatest magnitude. So if you think of it as pushing with more force, maybe. So think about this as 10 to the east, and this is 5 to the east. To add vectors together, we line them up tip to tail. Okay, so let's say we have, so tip, so here is my 10 vector in blue, and the tip of that is touching the red one, which is 5. The sum of the vectors is drawn like this. We add those up. So this has a vector of 15, magnitude 15 to the east. So when we have add a vector addition, these two vectors together, we have to add these together, but they're going in different directions. This one is going east. This one's going west. So again, we do the tip to tail on this as well, right? So this one, so if we could move this one here and put my red arrow here, right? It kind of makes it's a subtraction. So if this was 5 and this was 10, I would 10. This gives me 5 to the east. So we have to subtract those. Think about it in terms of you're pushing in one direction and the wind is pushing you back, or you're walking in one direction, the wind is pushing you from the west 5 and you're going 10, you are still going to the east, but you're slowing down. You can't move as fast because the wind is pushing you back. Can you put numbers on the magnitude too and subtract based on the direction? Think of a number line, right? So here they're going in the same direction. Again, the tip of this one here, we have 3. So we have a number line. So this gives us an 8. And it's 8 to the east. Right, got 8 for the east. Can you put numbers on magnitude 2 to add or subtract? Of course. Here we're going to do this. We have a vector of 5, and we put this vector that's going east, and the one that's going west is 3. We put those together. We have a vector that's going east 2 to the east. Add these 3 vectors together. All right, so we're going to put this one here. We're going to have a 9 going in this direction. 9 and 15 is 24. But then we're going to come back 3. So it gives us 21. Vector addition can be pretty complicated when we're using the tip to tail. But we're going to, that's for the next section of physics. When they get into, they have to use angles and cosines. So we're not going to get into that. Okay, it can get pretty complicated. Right, so if we were to add these ones together, right, tip to tail, so this one would go here, the red one would go there. Okay, the purple one would go down here. And the orange one would go kind of there. Okay, so vocabulary review. So we've talked about motion, right, which is a change in position. Position is our starting point or ending point. We need a frame of reference. It's where we start from. And again, a lot of times what we use is the X and Y axis to get us a position, right? So if I have a point right here, we give a couple of points to this. Like this one might be X is 1 and Y is 2. So the first point is always the X and the Y is the second point. Distance is our total pathway, right? Our displacement is a straight line between the start and ending place. Start and ending is a straight line, right? Quantity is a number or magnitude. Quantity is our numbers. Magnitude is how big. Scalar is just some number that does not have a direction, and vector is a number, a direction and a speed, or direction and a force, and we use arrows for these. All right. So we got to about 28 minutes, 30 minutes. I think that's pretty far for today. Right. Thank you much, ladies and gentlemen, and I will see you on Tuesday.